Okay, I've been asked about a pretty hard one here. It's really more about understanding what the author did in terms of phasors than it is so much about a circuit, I think. Let me explain. Here's the problem. It's from chapter, this is 33, I believe, and it's number 65. And the circuit looks something like this. It's got an AC source, and instead of putting it in series, as we've spent most of our time discussing, the three elements, the R, the L, and the C, are now put in parallel. So this, I guess, would fall under the name a parallel RCL circuit. Now, I want to use this as an opportunity to maybe emphasize a little bit more about the series RCL circuit. So let me pause for a moment from this parallel one, because I had made a comment somewhere in the lecture that it would be enough for us in our class to just deal with the series one. And that things that are in parallel or even more complex, maybe the inductor and capacitor are in parallel and then that group is in series with the resistor. We have the tools to do that, but they're kind of hard, although the three in parallel aren't quite so hard, as we will hopefully soon see, and that's what we're asked to do. But I do want to emphasize, as far as the exam goes, as far as this class goes, we're going to focus our attention on the series RLC circuit. So know that for the exam and for the homework. This problem, then, is really another way of saying that I wouldn't put something like this on the test. This is a parallel one, and it's actually pretty easy to solve if you understand phasors. So I want to use this as an opportunity to talk a little more about phasors, because phasors make something like this really easy to solve, and it also makes this really easy to solve. And so this, for most of you, this is your first exposure to phasors, and it's a really neat mathematical technique. I don't believe it's covered in any of the math series on phasors. It's usually considered an upper division topic, and so I know, and you transfer and you go into upper division, you're going to be asked to solve problems with phasors quite a bit, and I think it's really good to be exposed to it, because sometimes when at the transferring universities, the professors sometimes just go, oh yeah, you guys know these phasor things. And they kind of forget that, hey, it's your junior year, you're supposed to be learning these things. You don't know them all of a sudden. And you're supposed to know it by the end of your junior year. So you get exposed at the beginning and you learn it at the end. Anyway, so I think some exposure to phasors is good. And so that's why I was glad I kind of went through the series. And I want to kind of do that again. And once we really understand that, you'll see how easy this problem really is. And that's really what the author wanted you to kind of see, or at least what I wanted to see when I saw this problem. I knew this problem wouldn't make a good test problem, but I knew it would be a good one to make you think about phasors. And so if you could do this homework problem in about, 2.5 minutes, then you really got the idea of phasors. So let's talk about the series one again. And if you remember this whole discussion in chapter 33, we looked at resistors first, and we said that the current then would be in phase. That is, if you only had a resistor, and you didn't have these other ones, and the voltage was something like this, V max sine omega t, then if you had something as simple as a source and only a resistor, the current could easily be solved by taking the voltage, dividing it by its resistor, and it would be in phase, so it would be a sine function also. But then it got a little more interesting when we went off into the inductor. We said with the inductor, it kind of has that same effect that there is a opposition. I called it a reactance instead of a resistance. And of course, the reactance is a resistance from letting the current flow because of the electromagnetic effects. It's actually Faraday's law, and back EMF is produced. And we saw that this would be equal to omega L. We also saw here, and this is why we called it Eli effect, that the current and the voltage would no longer be in phase, and that the voltage would then lead the current. So if the current, and here's a real important thing between going to this one and this one, is since these are in series, we know that they all have the same current in them. So we could argue from up here that if the current is in phase with the voltage supply, so the voltage supply has a sign, so the current would have a sign, then the voltage, the EMF, would lead the currents in an inductor. So this would be sine, and the current then would be, I guess, lagging behind the voltage. But maybe I should say it the other way. The voltage then leads. Well, the way I wrote it, let's write these as separate pieces. Okay, so that would be the answer to this one. So this one, if the voltage has a sign, the currents would be behind it by 90 degrees. And so I would write the current as lagging behind by 90 degrees. And then let's think of this third option that we talked about before we put them all together, and that is the capacitor, which we referred to as the ice effect, because then in a capacitor, the current would lead. And so it would be the voltage divided by the reactance of the capacitor. Again, the reactance would be coming from the electric field that builds up between the plates because of the charges. And just like the inductor, we had the electric field that opposed it. Of course, this electric field came from the changing magnetic field. All right, so the inductor, I think, is a little bit harder to understand, but here is the electric field being opposed because of the buildup, and that's why you have to have the current first before you get the EMF. But in either case, then, if the voltage is following a sine pattern, then the current would come earlier, so this would be sine of omega t plus pi over 2, and the plus because the current leads the EMF in a capacitor. That's where those three letters come into play, just like the Eli. Now, knowing that, when you then are trying to put them together in series, you're trying to add different components, if you will. That is this. Well, let me come back to the picture. The sum of all these voltages, so the voltage on the resistor, the voltage on the inductor, and the voltage on the capacitor, would add up to the total voltage. The place where this gets kind of hard, though, is that the voltages are not in phase with one another. And that's why we went through this little discussion. So, in other words, if we realize that the current in all of these are the same, so if we write the current as some maximum current sine omega t, and the sine omega t is the important part, then when I go to write the voltage on the resistor, I would write it as, V on the resistor, okay? But then sine omega t. But then when I go to write the voltage on the inductor, I would say something like this, voltage on the inductor. And this is where I have to come back to my Eli effect. I would have to say that the EMF is ahead by, or leads, the current. So if you're going to say the current has a sine function, then the voltage would be sine of omega t plus pi over 2. And same logic for the voltage on the capacitor. So the ice effect is saying that the voltage is lagging behind the current. And I'll say it again, for a series circuit, the current would all be the same, so I would have to say that the current in the capacitor is listed as a sine function, so if it lags, this would be sine of omega t minus pi over 2. So what you're really asked to do in a problem like this is you are asked to really add 3 trig functions that are out of phase. Ouch. You could use some trig identities if you like, but still, ouch. So there is a mathematical technique called phasors. And so like I said, even though I haven't really got to the main problem here, but I wanted you to understand phasors here because we use the phasors when they're in series, and it's going to make this really easy to add up. And I'm going to also then use the phasors to add them in parallel, and it's going to make it, again, really easy. So let me just kind of review phasors. So keep this in mind, this page 2. And I want to add these 3 together. And I think the best way to describe a phasor is this way. And so I guess I'll call this a math. I probably shouldn't even call it a review because I don't think most of you have seen phasors. But this first part I know you've seen, so this is a review. If I were to plot a sine function, so if I were, plotting, and so here's time, and I have this function, let's just call it y equals sine omega t. Okay, so it's this one. Most of you probably think of a sine function as some kind of pattern like this. And that's not wrong, but it really doesn't go to the heart of what the early Greeks did. The early Greeks did this. They said, why don't we take a unit circle and tie a string right here on the unit circle and start wrapping the string around the circle. And in a process, let's make a plot. That is, on the vertical axis, we will plot how high is the string. So it's the same as this vertical axis. And on the horizontal axis, we will plot the length of the string. So the first point right here would be 0, 0. The length of the string is 0, the height is 0. And as you pull on the string, because it's a unit circle, this length becomes pi over 2. And eventually, because it's a unit circle, it's going to have a height of 1. And so it looks something like that. After a distance of pi over 2, the length of the string, it has gone up a height of 1. And then if you continue to wrap the string for another pi over 2, it begins to go down during that time. And eventually, after what I'd call a half circle, so a total distance of pi, it has come back to a height of 0. And the same thing repeats on the negative side of the circle. And so by this time, you've got a length of 2 pi. And so this plot right here is what I think most of you are thinking about in your mind when you think of a sine function. But what I want to do is draw your attention to this. This is at times, and this is one of them, a more convenient way to think about a sine function. Well, we like to think of it this way. Let me grab one of my colored markers. Let's see, I grabbed a blue one here. You could think of this as a little arm sticking out with a knob, and now this thing spins. And it's kind of hard to draw this spinning thing, but if you can imagine the tip spinning, and then you plotted how far did the tip move along the x-axis and how high is it along the vertical axis, this spinning arrowhead would be another way of representing this sine function. And I want you to think about a spinning arrowhead. This is called phasors. And so whether you think of them this way or this way, hopefully before this class is over and this video is over, you will think of them both ways. Sometimes people like to take like a little pointer here. So here's one broken pencil, and I can spin it. And I want you to think about this spinning arrowhead as a representation of a sine function. And I'm going to use that over here. It's going to make it really easy to add these together. In fact, a better visualization of this is on our website. And I was going to direct you there, but I go, you know what, maybe it's better just to kind of show you. See how this shows up on video. I put my laptop in tablet mode. Maybe I get a little reflection there, so I'll turn off the light. But I went to our Flash Physics here, and let me look for and sadly we only have a few with electricity and magnetism, and these old Flash animations are getting outdated. I noticed that even when I clicked on it, it said, hey, Flash animation is outdated, and said it'll only be supported for 1 more month. So it's been talking about dying, but as long as it's here, let me click on this one that says phasor, and this is the picture that I hope you have in your head. If I stop it, let's see, stop. You can think of a sine function as this old-fashioned way of going up and down, or you can think of it, which for many cases, like the ancient Greeks did, as a spinning arrowhead. Okay, and so if we kind of step through, you can, as I step through, you can see that here's the spinning arrowhead, and then there's a projection right here, which is just transferred to here for easy viewing. And so if you play it, the vertical arrowhead is copied over here, and then the horizontal axis is just kind of flowing with time, so you can see the sine function. So let me say it again to help you understand phasors here, that you could think of a sine function as just this kind of curve, or as a spinning arrowhead. And for this problem, I want you to think of it as a spinning arrowhead. And so if we kind of step through, step, 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 you'll see that the height here is projected over to here. And then, of course, the time axis is actually the distance the tip of the arrowhead moves. Okay? So that's this whole idea of a phasor. Now, I'm going to come back to this. And that's why there's a next on there. But with that in mind, let me turn the light on my desk back on. This will make a very, 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 did I say very, easy way to add three sine functions together. Because the first one is a sine function. So a sine function you might want to think of as a arrowhead. Maybe different colors could even come into play here. I'll start with the first one with a green here. So this first one here in green would be an arrowhead that would point out a certain magnitude. And so the length of that would be this maximum. And of course, it's a sine function. So you project it back. It has height of 0 now. And as time goes along, can you kind of imagine this arrowhead then spinning? And so this is going to spin. Now, at the same time, though, I want to add, and maybe I'll do blue for this one, I want to add another arrowhead that has a length of v sub L, and it is a sine function that is advanced by pi over 2 at the start. So if a sine function is pointing out like this, an advancement of pi over 2 would be an arrowhead starting off like this. A better name would be a cosine function. This is how, in my mind, it makes it easy to see a sine function with a phase and convert it into a cosine function without having to expand this out with your trig identities. There's another good example of how phasors can be useful. But again, looking at this pointing up, and it kind of spins around. Okay? Now, what that means, if I were just to add these two, now I have a third one to add, but if I were to add just these two, then I can just, like we did for any two arrowheads, two vectors, I would just add them together and it would be some kind of diagonal like this. And so the result of these two trig functions added together actually come down to a geometry problem. Just add these two lengths. And instead of a trig function, we have a geometry problem, just remembering that it's spinning. So we just add the two arrowheads. Now, of course, I'm not done because I have a third arrowhead. And so this third trig function, which I'll do in a violet here, notice it is saying it's a sine function that begins with a pi over 2 behind, a lag. So if I were to draw that, I would draw an arrowhead going down by, pi over 2. So it's not a sine function. It's a sine function reduced back by pi over 2. Just like this one here was advanced forward by pi over 2. And so, again, I hope you're seeing the power of the phasors here, because instead of trying to add these in some very difficult way of trig identities, I have now just taken three trig functions. And I'm going to then make little arrowheads out of them. And to get the result of these three, I just have to add these arrowheads. And so it becomes a geometry problem. And a simple one at that, because they're at right angles, compared to a hard trig problem. By the way, in passing, I will point out that notice how this must come out to be a negative cosine function. I know it's negative because, see, it points down and it starts off with a negative and then swings up to 0. And then as this arrowhead kind of swings around, you can imagine it goes positive again. So that's a negative cosine function, whereas this would simplify to a cosine function if I used a trig identity. And again, I noticed that just by looking at the picture. And so that's why I can always just kind of look, okay, if I have a sine function, offset, draw an arrowhead, boom, oh, that's a cosine, or that's a minus cosine. So the phasors are really neat tools, very, very neat mathematical tools. Okay, so keep this picture in mind, because I am going to add these three together. But in the process, and I'll say it again, of adding the three, I am not going to do any trigonometry. I'm going to do geometry. Okay, so where'd my red pen go? Here it is. If I go to add these three, why don't I start with this light blue one and the violet one here? Because to those two, I would just, one's up and one's down. So this was supposed to be representing the voltage of the inductor, and this the voltage of the capacitor. So those two together would be VL minus VC. And those two together would represent something that in a picture might look like this. Let's just say VL is a little bit bigger, so I would get maybe this much out of it. So this right here is VL minus VC. And then, of course, I still have to the side the VR. And so if you turn it into geometry, since they're at right angles, the result of those three arrowheads added together, so these two are in the same direction. Well, they're in opposite direction, but they're along the y-axis, so I subtract them. So this is the resulting y component. And then the r is the x component. And we know from geometry, if you take the x component and the y component, Pythagorean's theorem, you'll get the result of those two that are added at 90 degrees. And hence, ta-da! And then, of course, you could eventually switch this into the resistance of the inductor, the reactance of the resistance of the resistor, the reactance of the inductor, and the reactance of the capacitor. And that's where we got our impedance. So I kind of went quickly at the end to talk about the series LCR circuit, but that wasn't, and purposely, that wasn't my point. My point was to give you a little more insight into adding these vectors together, or these arrowheads. So the result may look something like this, and then spinning. And so you would say that this is its magnitude. It's still spinning, so it's sine omega t. But it may have a little bit of phase, and that little phase we can get, again, from our geometry, although I guess this is some trigonometry, because I'm going to say if that's the phase phi, because remember this line represents the current, then this would be the tangent of phi would be this height. And so that would be VL minus VC over the x direction, which is VR, which we can then simplify to XL minus XC over R. And that's where these little formulas came for figuring out then, this is called the impedance here. We added the phasors, and this is where the angle came. And so what looked like was going to be hard to add these three together actually became real easy. There it is, plus inverse tangent of XL minus XC over R. Ta-da! And so these three, 1, 2, 3, added together is equal to that. And I got that most by looking at the spinning sticks, the spinning arrowheads. That's its magnitude, and then that's its phase, and it's the phase from a sine function. Okay? So that's the neat little trick. In fact, I'll bring the laptop back in front, or I guess it's in tablet mode, so I don't know what to call it, a tablet or a laptop at this point. I never really use it in a tablet mode. This is really my first... No, I've done it once or twice. But anyways, so this is our phasor. Let me go to the next one, and you'll see what the author is trying to say here. He's trying to say, look, if you look at two of them adding together, and so he's got a green one and a blue one spinning. Now, if you look at it, what I'll call the old-fashioned way, you would say the blue has a sine function and the green is a sine function that's out of phase by phi. Maybe I'll stop it here. Let it go back a little bit. By the way, it keeps getting bigger and smaller. Like I said, I never really use it this way. But anyways, you can see how it's spinning along. And we have then the sine function, although minus sine function here. I wonder why that has a minus sine function. Oops. Well, I won't worry about that now. But anyways, I wanted you to see the phasors there because, in fact, let me get away from this one. This one's getting harder than what I really want you to see. Let me go back and do the phasors that are actually related to our class here, the LCR phasors, and this is in series. And so here's what Don put together. He said, look, if you just want to look at an AC signal and a resistor, they would be in phase. And so he's got the current and the voltage here. The current is in green and the voltage is in red. And you can look at them as an old-fashioned sine wave if you want, but for this particular problem, I want you to think about them in terms of this phasor here, okay? And so they're a spinning set of arrowheads, a red one for the voltage and a green one for the current. But notice they're in phase because then if you look at just the inductor by itself, you would have something that looked like this. You would have the voltage, that's the red one, leading the green one. And so you could think of them this old-fashioned way here, but you could also think of it as this spinning stick, okay? Or sticks, one for the voltage and one for the current. And the same thing for the capacitor. But of course, for the capacitor, as you can see, the green one is ahead of the red one here as it spins around. And so in this one, we get currents before we get voltage. There's the ice effect. Okay, and so he writes it as a lag, but the voltage lags the current, or the current leads the voltage, whichever way you want to phrase it here. Okay, but that is the whole idea of them separate. And here's where he should have made some spinning ones in an animation, but this is exactly what I was trying to show you, is that then if I wanted to add these three voltages together, so we're adding around the loop, you would add the voltages, and to give you a reference point, you'll put a green one for the current, because again, the currents are all the same because they're in phase. Keep that in mind. I'm still need to do the problem for you, and I want to know what's the same. That's our reference. So in this case, the reference is the current, and so the voltage is in phase with the current for the resistors. So I just drew a red arrowhead in the same direction as the current. Here the voltage leads the current, so we're making a red arrowhead, V sub L, and it's ahead of the current. And then, of course, the voltage here lags behind. So I made an arrowhead going down. And so the question is, if you add those three red arrowheads, if you want to add up the voltages, so I want to add up the three arrowheads, how would I do that? And so you can see, as I was trying to show you on the paper that is that I guess the first thing I would figure out the y component. And so it would be VL minus VC. That would give me the y component. And then since the VR is the x component, I would use Pythagorean's theorem. And so, yeah, that's kind of what he gets at here. And at this point, I don't know if he does really what I want you to see, so maybe I'll just go real quick. But this might be the better of the two. You would subtract the two to get the vertical one, and then the horizontal. All right, well, let me put this away here. And like I said, hopefully, even though I was kind of long-winded about it, this was a nice chance for you guys to see phasors again, because I did them in the video lecture, but it was really kind of fast, and I know it's the first time. It's kind of hard to digest that. So when this problem came up, I thought, this will be a good idea to take a moment to talk about phasors. All right, now finally I can get to the problem. So let's come to the main problem. Here it is. This problem is number 33, or number 65 in chapter 33. And if you look closely at it, it looks like my computer went to sleep, so let me turn that back on here. But I would say that this one where they're in parallel, is a lot like this one that's in series. Now, series, they had the same current. So over here, I would say they have the same voltage. So let's do this. Let's make a phasor diagram. And let me do a reference. And instead of the current being the reference, let's have the voltage be the reference. So let's say the voltage is behaving this way. There's a volt max sine omega t. So in your mind, I hope you see this little arrowhead, and it's spinning around. And so that's the voltage from our source. Okay. And I'll say it again. All of these have that same voltage. Now let's look at the current from each of them, because this problem is asking you to find the total current. And the total current would be the current in the resistor plus the current in the inductor plus the current in the capacitor. Okay? And these would not all be in phase. These are going to be like we just did, although when they're in series, I added up the voltages to get the total voltage. Now that they're in parallel, I'm going to add up the currents to get the total current. But what we're going to see is there's a phase relationship that we've got to accommodate here. So let's talk about the currents that would go through this resistor. It would be V max divided by R, and it would be in phase with the voltage. And so if the voltage is a sine omega t, the current would be sine omega t. Okay. Now let's talk about the current in the inductor. The magnitude of it would be V maximum divided by the reactance of the inductor. Okay, so X sub L. And then it would be sine. Ooh. And now we know for the inductor, they're not in phase. In fact, for the inductor, we use the phrase Eli. And so this says the current is behind the voltage by pi over 2. See? So if the voltage is sine omega t, the current would be behind it by pi over 2. Okay, if I add to it now the current from the capacitor, that would be V max over X sub C. And then it would be sine omega t. And the same logic, we like to think of our capacitors as ice, meaning the current is before the voltage. So again, if we're using the voltage as our reference, as a sine, the current then should come before that. So be plus pi over 2. Okay. So this is the part where I'm using what we've learned in this chapter about the current. And so this is the Ohm's law out in front, and then this is the phase of them. And now I'm asked to put these three trig functions together to get an equation for the total current. And that's what A is saying. It says, what is the equation for the total current? So I've got to add these three. And instead of adding them with a bunch of trig identities, I'm going to use this technique of phasors that I babbled on about for 30 minutes, and I'm going to add those together. So let me draw a phasor diagram. Maybe I'll put the little arrowhead that represents the voltages in here for a reference. So I'll do this as the little arrowhead. This will be the voltage one. But let me go to my different colors. And so the resistor one, the current, would be in phase with that. So it would stick out in this direction. It would have a value of V over R. That's the magnitude, and it's in phase. Okay, so there's my first arrowhead. And so imagine that thing spinning. Now for the inductor, I'll do a different color. Maybe I should try to match it. What I do, I think I did the blue for the inductor. Okay. This says it has this magnitude, and it is negative. So it would be represented with an arrowhead going down to start, and then it would spin. So it would start when time is 0. It would start at negative pi over 2 and then spin. Okay. And it would have a value of v over xl. That would be its size. And then the other one, which I'll do in kind of this violet, would be the voltage, the current from the capacitor. That's this term. And so again, notice it's a plus pi over 2. So at time equal to 0, the arrowhead would start right here, and then it would begin to spin. And it would have a length of v over x sub c. So this is this little trick with the phasors. And so instead of trying to add these 3 trig functions together, I'm going to add these 3 arrowheads. Okay. So how would I add those arrowheads? Well, I think you can see the y component would be the v over xc minus v over xl. That would be the y component. The x component would just be the v over r. And so when you add x components to y components, you use Pythagorean's theorem. So this would be the maximum current. If we do some more math here, such as factoring out a v and put it in front and factor out a v here, or v squared I should say, then each of those factored out, I would get a v in front, and I would have a square root of 1 over r squared plus 1 over xc minus 1 over xl squared is the maximum current. And finishing part A by saying this is 1 over r squared. The reactance of a capacitor is 1 over omega c. So I'll just go 1 over x sub c is omega c. And then this is 1 over omega L, and I will square that. And then this would be the maximum current if I put in maximum voltage. I see in the answers they want you to get the RMS current, which is what you would get when you put in the RMS voltage. So there's the answer that they wanted. And even though it took me a long time to explain it because all that phasors, I'm hoping you see how quickly this problem could have been. All I had to do was write out that the sum of the currents and the different phases, write out the 3 sticks, and do a little geometry and Pythagorean's theorem, and I get the answer to A. And I also get the answer to B, although I'll show it to you. How do I get the phase between them? And so if you imagine this one's a little bit bigger than that, so the result will be kind of a small vertical piece, and I add it to this horizontal piece, the result would be something like that. And so if we call this the phase, so we say the current then is, in this case, it looks like a positive. The current leads the voltage, because remember, this is our reference for our voltage. Of phi, I could write this as tangents of phi is then equal to the opposite, and so that's the difference between these two. So v over xc minus v over xl over the hypotenuse, which is v over r. Now, they each have a v in them, so I could factor it out. So this becomes 1 over xc minus 1 over xl all over 1 over r. And then if I flip this, this becomes r in the top, and this becomes 1 over xc minus 1 over xl, and that's where they stop for the phase, although you could go and say, well, 1 over xc is omega c, and this is 1 over omega L, might be the next natural step to write it in terms of the capacitance, the inductance, and the frequency. And, of course, what that would ultimately mean here is that I could write the current in this parallel circuit as its maximum, and so this would be V times the square root of 1 over R squared plus, let's just do this one here, omega C plus 1 over omega L square root, and there's a square, okay, and then sine omega T plus the phi, and the phi is right here, so that's inverse tangent of R times omega C minus 1 over omega L. Yay! And so that is the current in an LCR parallel circuits. And I got that by, again, phasors. I could get that same thing right here, all this messy stuff, by doing some really hard trig identities on this and pages of mathematics in order to get here, but the phasors make it so much nicer. So I hope I didn't talk too long. Hopefully you see how easy the problem is once you understand phasors, but more than that, hopefully the first 30 minutes give you a little more insight to phasors so that when you see them in your future, you're not quite as shell-shocked. All right, bye now.